Hombre, sí, sí, sí. Si no está muy ancho.
Estos son los que hemos
En teoría, antes de que por lo cual, las cosas son así. Por eso la hice fabricante.
Esa es la versión que esperaba.
Ah, bueno, no. Me tranquiliza.
Welcome to the Mañanas. It's a pleasure for me to introduce you Álvaro Chavarría. He's originally from Costa Rica. He did his bachelor in US, and then he got a PhD in Princeton University working for the experiment for Xenon that was doing neutrino physics. And then he got a fellow in the Kelly Institute in Chicago to work in DAMIC and DAMIC-M. And now he's professor at the University of Washington. And he's a spokesperson of DAMIC, and he's detector deputy of DAMIC-M. And he is also the spokesperson on an experiment called Selena that is looking for neutrino double beta decay. So he will tell us about the progress in DAMIC and Selena.
Okay, thank you, Rocio, for inviting me. This is the first in-person seminar given in a long time, so I hope I'm not too rusty. And thank you for the introduction, because I will talk actually about those things, which is DAMIC, which is an experiment I've been working on for, well, almost 10 years now, and an R&D project that we have called Selena that is for different types of imaging sensors. So here's the outline of my talk. It's maybe it's a bit long, maybe it's a bit ambitious. But I'll talk about the two things that these experiments have in common, which is the use of high-resolution pixelated charge sensors on solid-state targets. And I will mention the advantage of these sensors in terms of noise and background suppression. Then I will talk about both the experiments. First, dark matter. I'll give a very brief introduction to dark matter. And then I'll talk about the resultant dynamic at SNOLAB, which has been running underground at SNOLAB since 2012. But mostly R&D until we did good science run from 2017 to 2019. I'll talk about the progress toward DAMIC-M experiment, which is a bigger experiment. And then I'll go into just this new idea of Selena detector concept and some science that we could do doing a spectroscopy of double beta decay and solar neutrinos. So here is the very basic sketch of what we're doing. You have a pixel array coupled to a thick target. The target is usually just a region where you apply an electric field and you can collect any charge produced in the target on a pixel array. So here you have an ionizing particle, goes through, frees up charge in your, call it a photoconductor, then you drift the charge, you collect it on the pixel array. Usually we're working with things that are maybe order of a millimeter thick, and the pixels are 5 to 25 microns, so this is usually the size. And one thing that is most important for DAMIC is that you have charge diffusion as the charge is drifted up. And so when you have, this is what astronomers call the point spread function. When you have a point-like interaction in the, say, the silicon, you end up with a two-dimensional Gaussian in the pixel array. And this is what allows DAMIC to do reconstruction in depth. And then you get, of course, XY from the pixel position. And then I will mention that it's not only ionizing particles, but also just thermal excitations in your target will produce, it's called dark current, just free electrons that are a source of noise, and this is a problem. The nice thing about these devices in general is that, or what is different, is that we don't need to, when you're doing Fourier event searches, you don't need to run fast or read out fast, so you can actually read things quite slowly, which improves your noise a lot. Okay, so you hold the charge and then you read all the pixels to make an image. The charge measurement, really, the reason why the noise can be quite low in addition to the time is because the capacitance of the sense element is just very low. So the idea is that you put charge here, you measure the potential there. The potential difference basically between a capacitor and across a capacitor. You know this relationship, right? The charge you put in the capacitor is proportional to the potential across it with a proportionality constant is just the capacitance. And so if you have capacitances that are slow, say 10 femtofarad, then you get measurable potential differences, even for small amounts of charges. And the way you get small capacitance, there are different ways, but the way you do it, in our case, you just make the thing small, right? If you have a parallel plate capacitor, then it just goes with the area over the distance. So the capacitance scales linearly with the overall dimension of what they're doing. And so when you do, say, microfabrication, you make something that is micrometers in size, capacitors that are micrometers in size, you get femtofarad. And then you get something that you can measure. And then the strategy for measuring is mostly, you can do this in generally. It's very important for DAMIC. It's called a correlated double sampling, where you basically measure, you reset the value of the amount of charge you have in the capacitor, you measure it empty, you put charge in, you measure it again, and then the difference gets rid of what we call reset noise, which is just resetting the switch after every pixel measurement. And then you measure like this, the delta V, which is what gives you the charge difference. And one nice thing is that you can integrate both the reference and the data level for long times to filter out high frequency noise, okay? If you have to run very fast, you cannot integrate for very long, so you're more susceptible to high frequency noise. And so here is the general scheme of these sensors. So you have a particle, it deposits energy in the target, you generate the charge is drifted and collected on the pixel array, and then you can do two things. So when you have a charge coupled device like DAMIC, you physically transfer the charge across the pixel array to a corner of this rectangular device where you do the charge measurement. Charge to voltage conversion, and then you digitize it, and then you get your image. When you have like something like it's actually a picture of a depth fed, but it's also the same with a CMOS active pixel sensor. You do the charge voltage conversion on the pixel, and then you do the signal transfer. So instead of moving the charge is measured in the pixel, and then you just have a series of switches or registers where you can select which pixel you're reading out, and you can read it out serially and construct an image, and then you end up getting things like this. So this is if you take an image of CCD image in the surface lab for 15 minutes in the dark, so you're not really imaging anything. You get mostly background noise, but you immediately see particle tracks in it. So these are beta particles, X-rays, muons. Here just a zoom. This is just an image from a DAMIC CCD. You can get the amount of charge that is collected per pixel is proportionally to the energy deposited. So here's the energy scale in color. 50 pixels, you can see an electron. You can see, by the way, here the Bragg peak. This is where the electron ends, so it starts here. And this is a muon, a straight target alpha, and things of this sort. So you have very nice particle identification capabilities at the, say, MeV, tens of keV to MeV scale of energies. Okay, I don't know why it's not going next. Let's continue. Okay, it's working now. So this allows you to do identification with the imaging capability, so you can determine the particle type, muon, a high energy beta particle, or an alpha particle. You can determine the endpoints of the beta track when you find the Bragg peak. This will be important when you're doing double beta decay. Not so important for DAMIC, but you can do it. And one thing that is very particularly special is that because the atoms remain mobile in a solid target, you can identify radioactive decay sequences, which is the main background in these types of low energy searches, with time separations that are very long. So if you go and look at a recent paper by DAMIC, we use this strategy to constrain the decay rates of basically every beta isotope in the uranium and thorium chains. So if you know, uranium and thorium are the primordial elements that constitute most of the background for basically astroparticle and nuclear physics and low energies. And you can actually do very well identifying those particles by looking at these spatial coincidences. This is what I mean. So this data from DAMIC. So there is a very common isotope that worries us, which is lead-210. Lead-210 is a contaminant mostly on the surfaces of everything for materials being exposed to radon in the air. So lead-210 remains on the surface of things, and it has a sequence of decays into bismuth-210 and polonium-210. Okay, but usually, I remember when I was in Worksina, we had a very big problem. Bismuth-210 was our main background and something that was basically unsurmountable, we thought at the time, or at least because you couldn't tag them. And the reason was because in a liquid, you can maybe have the different decays, but things move around, so in a period of days you lose track of where the particle was. Now when you have a solid state target and very high pixelation, the probability of 3 decays happening exactly the same position is negligible. Okay? So here you can see that even though these decays are 4 days apart, this is the entire lead-210 decay sequence. Lead-210, bismuth-210, polonium-210. Okay, and we can do this for other things. One of them that was very, very problematic for us originally was silicon-32, because silicon-32 is an isotope in silicon that you cannot really purify away. But silicon-32 decays into phosphorus-32, and so again, you have a decay sequence. So even though this background could be problematic for silicon sensors, for DAMIC it's much less so, because our higher pixelation allows us to detect the sequence between silicon and phosphorus, and then you can tag them. And this is also in the paper that I mentioned. And here you can see again, phosphorus-32, betas are quite high energy, so you get that nice bright peak at the end. Okay. So let me talk a bit about DAMIC. That was kind of like a flash introduction to these types of sensors that we use. Is there any questions now, maybe? Yes?
Since you were talking earlier about charge,
yes.
How do you convert that charge to the energy that you see in your graphs here? So you have a conversion from charge to energy, right there, for example, in the inset.
Yeah, so that is done by, there are different ways to do it, but usually you calibrate with an X-ray source, and you get how many electron hole pairs you get, say, for 5.9 kV from iron 55. This eventually gives you about 3.8 electron volts to make one electron. So you just divide by, you multiply by 3.8, and you get that value.
Okay.
For nuclear recoils, it's trickier, and I'll mention that briefly later. Okay, so dark matter. So there's dark matter in the universe. It's basically seen by the dynamics of objects everywhere. This is the original way to find it, which is basically if you look at the motion of a star around a galaxy, and you try to solve what should be its rotational speed based on the amount of matter that is within that radius, then you get something that doesn't agree if you estimate the mass of the galaxy just by counting the number of stars and estimating the quantity of gas. So it seems that there is a contribution to this centripetal force that a star feels around the center of a galaxy from some substance that has some mass, but we don't know what it is. And there's evidence, again, from cosmology, formation of galaxies, cluster of galaxies, gravitational lensing. Other people know much more about this. Basically, the universe wouldn't be as compure as it is if it weren't for the existence of dark matter. So we have this substance, which is called dark matter. And this matter is very much matter and discovered as matter in one way, which is that it bends, space-time, just like matter does in general relativity. But if you think about matter, there's a second definition, which is that matter is made of, corpuscles, sort of, building blocks, what we call particles. And so when we people talk about direct detection, we're talking about the way to discover in dark matter this correspondence in the second sense, seeing what is the dark matter made of. And I think it's a profound problem, maybe more than people appreciate, that challenges the very notion of matter. But what I'm going to talk about is basically a very standard approach. We just assume that matter has these both properties, and you're looking for it. But I will just say, especially if there are young people in your audience, that this paradigm might not be correct, and maybe the answer is more revolutionary. But I don't know too much about it. So what type of particle could make the dark matter? So this is just an inference. Everything that has matter is made of particles, so we assume dark matter also. It cannot really interact with photons directly, really can have a measurable electromagnetic charge. It has to be stable because all matter was created early in the universe. It has to be, for it to be here around us, it just cannot decay at cosmological timescales. It has to be slow enough to clump and form the dark matter halos around galaxies. That's what we call when we say dark matter is cold. And no known particle has this property, so we say it's dark matter. Dark matter really is not a problem. It's a problem from cosmology, but it has huge implications for particle physics. So if you were to look at this in the lab, dark matter signal has local density, small interruption cross sections, is cold. And you need basically, because it's cold, the speeds are very low. And so its kinetic energy is very small. So you need what we call a low threshold detector that can detect the small energy signals that would be deposited by the dark matter. So here is the traditional dark matter nucleus elastic scattering, which is the traditional mechanism for WIMP searches, where you have a WIMP gives a little kick to the nucleus carries the energy, it deposits, ionizes charge in your sensor, and you see it that way. Here there's some formula. The point here is that the lighter the WIMP the less efficient you are in transferring energy to the nucleus. So this is like the case where it gets so light, it's like a ping pong ball striking a bowling ball, and the wind goes back, but no energy goes into the nucleus. So here's an example. Here you have a case for silicon. You have 100 GeV WIMP, gives you quite a bit of energy, but 10 GeV gives you less. And so this is how people were looking for dark matter maybe since the beginning of the century about. And then maybe in the last 5 years, people have started thinking about new ways to do it. And so if you were to look at a plot, this is sort of an old plot, but it's characteristic of the exclusion limit. So here's the WIMP mass, here's the cross section. You would have, say, a high mass search or low mass search, but you see that even if you use a lighter, this is a silicon target, this is a xenon target. A lighter nuclear target gives you more sensitivity, but eventually, again, you start losing sensitivity because you get to this regime where it's just like bouncing off the nucleus without giving any energy. Now, we have in materials a lighter target than the nucleus, which are the electrons. And electrons are not like nuclei in the sense that they're just there. They're actually going around the nuclei with some momentum. So when you have a dark matter coming in, you can scatter with an electron, and you can also, and even if the dark matter is very light, you can always find the correct, it's a probability of fitting in the correct phase space to basically ionize an electron. So when you go to a lighter, when you use electrons, especially in semiconductors where the band gap is almost 1 eV, then you have sensitivity to dark matter masses that go, to 1 MeV or so. Okay, so you covered this region of parameter space, and this is actually quite, for the last few years, this has been explored extensively in the literature if you want to look into the archive. And so this is good for us because silicon has quite a low band gap, and we detect electrons quite efficiently in CCDs. So it makes very attractive for DAMIC. I'll give you a bit of historical introduction because there's actually a interesting thing is that when you try to make new things, new experiments, the best way to do it if you're lazy, in the sense that you take something that already exists, and so you don't have to develop it from scratch. And you'll see this is both the case for DAMIC and Selena. So CCDs are still used for digital imaging. Actually, the Nobel Prize in 2009 was given to Boyle and Smith for inventing this device, which what it really did was revolutionizing astronomy because it made digital imaging possible in telescopes. And so they look like this. The idea to use DAMIC or CCDs for dark matter came from Juan Estrada's Fermilab, where he was working in this thing called the DAMIC-M. And they needed CCDs that were very sensitive in the infrared, or in the red wavelengths. Yeah, I guess it's infrared. And so they made the silicon very thick. But when you make the silicon very thick, then we're talking about 0.5 to 1 millimeter or so. Now you have a bigger target, say, that could be used for dark matter searches. So this was something that was developed for a different reason. People realized, oh wait, these CCDs are so massive and so sensitive that we could also use them for dark matter. And we started then characterizing them as particle detectors. Okay, so you can see here, this is just based on taking advantage of the diffusion to reconstruct the depth of these things in the detector. So this is the back of the CCD, this is the front of the CCD. These are iron lines from iron 55, and you can see how we can tell very well when the lines are in the front or on the back of the CCD. This is another example of diffusion. When a muon goes to your CCD, where the track goes through the back side, there's more diffusion, so it looks fatter here, and then just very thin at the front. And then you can use, again, these still are light sensors, so you can actually use optical photons to calibrate the signal that you get even to quite low energies, 40 electron volts. And then there was a huge effort that we undertook maybe 5 years ago in Chicago, which was to calibrate the signal of nuclear recoils. So if you remember, the standard way to look for dark matter particles is to look at the energy of the nuclear recoils. Now, nuclear recoils, a nuclear recoil of 1 keV does not give you necessarily the same amount of energy as an electronic recoil of 1 keV, basically because the interactions are different and their energy losses into phonons and things into the lattice. And so we actually did an experiment with a neutron source, and we were able to basically take inject into the CCD a spectrum that is very similar from a 3 GeV WIM, and with an endpoint of about 3.2 keV, and we were able to fit the spectrum to get this relationship between the what we call the electron equivalent energy, which is the energy deposited by electrons, and the energy deposited by nuclear recoils. So far, the threshold of this measurement remains basically unmatched, and it makes at least our WIMSER results some of the most, I think actually, at low mass is the most reliable. And then we also could use this data to show you that we reproduce also well the reconstruction of the depth of the interaction. So this is just the spread of these clusters in the CCD and how the simulation matches the data. And so we did first work at SNOLAB, so this is how the detector looked sort of in the end. This was a 4K by 4K 16 megapixel CCDs, about 6 grams. They're in a copper frame with a flex cable that brings the signal out, and they slide into slots of a copper box. That copper box goes inside a lead shield and a cryostat, because these CCDs need to run about 100 Kelvin. The reason we need to cool them down is to stop dark current noise. So if you want to be able to see this very, very sharp clean images and low, then you need to run relatively cold. It's a small. Here, this is actually Jing was the first DAMIC grad student. She graduated again many years ago. And this was just to show the scale of things. This is the lead shield and the poly size at SNOLAB. And we did quite a bit of science with this. So we did, let me just talk first about the first results. This is called the leakage current analysis. So this one, the idea was that you would look at the pixel distribution. So here in this histogram, you just have the value of every pixel. And most of them are just noise, but you have some additional noise as skewness, right, from a pixel that collect charge from dark current. Okay, so by looking at the tail of the distribution, you can see how much leakage current is being generated. Okay, and it's actually quite low. It's something like 2 electrons per millimeter square per day. Now, if there were an additional source of charge, say from a very light dark matter particles scattered with electrons, then that would sort of increase the amount of this leakage current that you see. And so even though you can't really discover dark matter this way, you can put an upper limit on the flux of and the cross section of dark matter scattering with electrons. So that's what we did. These are CCDs were working very well. We're getting 1.6 electrons RMS of noise, and here you see what our fit was. And then if you had, say, a dark matter electron scattering with 10 MeV, then you would see something like this. So we put limits for that. So you can see those limits here. Those appear in 2019. The limit had been surpassed right now by Sensei, but they were the best when they were published. And then also we used this technique even before Sensei to place the first exclusion limit from signals in this EV range. There was a paper on hidden photons from 2017. Okay, but these are org results. Let's talk about the more recent stuff. But the main goal of DAMIC originally was doing a WIM search, which we just completed last year. So we have 7 CCDs, 40 kilograms target mass, 40 grams target mass, collected 11 kilogram days, a 50 EV latitude threshold. And the strategy here, this is actually what one event looks like. So if you wonder about how 140 kV, 140 EV 140 EV event looks like in DAMIC, it looks like this. You have here your baseline with 2 electrons of noise, and then you have a very, very clear event with 140 electron volts of energy. And so basically we looked at all of these low energy events. We made an energy histogram, and then we compared to some background model based on all the contamination from radioactivities in the detector. And this is roughly what it looked like. So we did this 2-dimensional fit. So again, this is the energy, and this is the spread of the clusters, which tells you roughly how deep they are occurring in the CCD. So you have events from the backside here, events from the front here, and then here is mostly from small angle Compton scattering from gamma ray backgrounds. And then we did a full analysis, starting with the radioactive contaminations. In every detector component, we get basically this spectrum. And then we actually we saw a bit of an excess, which I'll talk about, but otherwise, above 200 eV, the background model matched the data perfectly. So here are some details on this excess. So we saw 17 plus or minus 8 events. They are fit well with an exponential decay spectrum of 70 electron volts. And actually the presence, the significance of this excess has a p-value of 2.2 times 10 to the minus 4. So it's quite high, and here you have a counterplot on the energy of the decay length, and the signal amplitude. And here it's just with the background subtracted. So this was reported in a very recent publication, which is very long. I spent maybe 2 years with some good group of people writing it. Rocio helped a lot writing this paper and reviewing it too. And the bottom line is that the events really look like they're in the bulk of our CCDs. We really have no statistically significant features in the spectrum besides the low energy excess. Basically, the data matches the background spectrum very well above 200 eV. And so far, no known background or detector response hypothesis are going to explain this. But then, of course, there are the known unknowns. So, maybe there's some defined noise source. Maybe it's an imperfect background response model. We don't know if these are nuclear recalls or electronic recalls because at very low energies we can't tell those two things apart. So in spite of the presence of this excess, we could use it to place an exclusion limit for WIMPs, which was a PRL last year. And this was basically the result from DAMIC-M. This is what we set ourselves to do. And then it was published last year. And maybe the most interesting thing is that there was an excess from a previous silicon experiment called CMOS to silicon, which has never been probed with the same nuclear target, and we do this for the same time. This is relevant because depending on your dark matter models, the signal can look different between different nuclei, xenon, silicon, germanium. So having two silicon experiments look at this region is quite useful. So we rule out some of their parameters, especially at low masses where it was easier to reconcile with other experiments. Okay, any questions about DAMIC at SNOLAB? Yes?
You work at 100 Kelvin,
yes.
Isn't it? And this temperature is through nitrogen. You have a nitrogen bottle next to the experiment. I thought I saw nitrogen there.
Oh, yeah, that's a nitrogen for something else. Ah. So we use a cryomech cryocooler, and maybe 100K is too, I had as an order of magnitude. Actually, we run most of the time in DAMIC at SNOLAB 140K.
140.
But this nitrogen bottle is actually for using nitrogen gas to purge the lead shield from radon. Because if you don't have it there, then radon gets in the holes in your shield and then gives you, regular air has radon, it gives you gamma rays, it gives you background. So this nitrogen bottle is actually for removing the radon around the thing.
Okay, thanks.
The purge is done constantly, or you do it?
It is constantly. It has I forget the units, but there's a constant flow of gas through the shield. Okay, so then so this was DAMIC at SNOLAB. Then we're moving about a bigger experiment called DAMIC-M. This is a very ambitious project. It's a direct collaboration between North America and Europe, and that includes Rocio's group here at IFCA in Spain. We have 50 CCD, the goal is to, we don't have them yet, but the goal is to put 50 CCD modules at Modane Underground Lab in France to get a kilogram year target exposure. So there's a factor of 100, more than 100 more than DAMIC at SNOLAB. We plan to have a huge improvement in noise. Instead of 1.6 electrons, we're going to use what they call skipper CCDs to get single electron resolution and get much sub-eV basically noise, so that allows us to go from like 50 electron volts of threshold to something like 5. Okay. Of course, if you increase your exposure, you don't gain much if your background is not also lower. So we have a background. Our goal is to get the background to a fraction of DRU, and the main challenges, and I will not talk about them now, but there's a huge program to mitigate contaminant activation, surface contamination, and detector response, and understand and improve the detector response. Here's just a picture of what this thing is going to look like. So you have your cryostat, you have your CCD array, you have some internal shielding, you have some flex cable that bring the signals out. There's also a heat exchanger here that will actually be circulating nitrogen to cool, so this will be different than DAMIC at SNOLAB. And this is just what the current design of CCD array looks like. So each module is made of 4 9-megapixel CCDs that are glued in a silicon carrier, and then you have a flex cable here that brings them out, that brings the signals out, and they're put in this. The 52 of them are arranged in this basically configuration in 4 bundles around the cold pipe. Everything here is made of electroformed copper. Everything is going to be very pure. It's going to be very quiet, very cold, and then we'll hopefully be able to select that. Here, just things of the DAMIC-M science. So this is in MeV scale, GeV scale, electronic recalls, nuclear recalls. You can see how well we can do. This might still be the latest sensor limits, I think. But you can see here that we will be able to do orders of magnitude better than anyone else in dark matter electron scattering and MeV range. And in the GeV range, we would also improve significantly over other experiments. Okay? The years are previously dynamic at SNOLAB, so it will be a huge improvement. So let me talk a bit about the skipper CCDs we're using. So the idea here is that I talked about how we measure, when we do this correlated double sampling, we measure a potential difference to get the charge on the pixel. Now the idea here is that because in the CCDs you can move the charge very efficiently, and you can assume that given that we can actually move charge on a device that is 9 by 9 centimeters square, we can really get it to the corner. You can move the charge millions of times along, well, actually not millions, thousands of times along pixels to get them to the output amplifier that we could actually, so we do basically, we call it a charge transfer efficiency. And we lose basically 1 electron every million transfers or so. So when you make the measurement of the charge, you can actually move the charge in your, what we call the sense node, in and out of it, and repeat the measurement with the same amount of charge. As long as the noise in those measurements is uncorrelated, then the averaging just gives you better and better resolution. It goes when you do n uncorrelated measurements, your noise goes with 1 over square root of n. So this is what the skipper readout does. It was technology proposed in the 1990s, and a few years ago, the Sensei collaboration were the first ones to deploy one of these sensors to do dark matter searches. Now we have our own in DAMIC. So this is just our single electron resolution in our DAMIC-M CCD, 0, 1, 2, 3 electrons. So remember, before it looked like a Y distribution with 1.6 electron RMS. Now you have 0.07 electron RMS, and you can count the peaks. We packaged more than 50 CCDs at SEMPA. This is my institution at the University of Washington of various formats. We completed packaging and testing the first prototype run, and we're currently packaging and testing what we call a DAMIC-M pre-production run. So the first batch of these 9 megapixel sensors that are not meant to do science, they're just meant to make sure that they work well. But you can see here some photographs in our lab of the CCDs being packaged. These are some large prototype CCDs, 6K, 6,000 by 4,000 pixels, 6K by 4K, and these are just pre-production CCDs. Not in the module, but individually packaged just for testing. So the 6K by 4K CCDs, these are actually these are from the DAMIC prototype run. So the first one that will go underground. Actually, 4 of them are already underground. They're massive. They're very big, 24 megapixels, 9 by 6 centimeters squared, 10 grams of silicon each. We packaged 22, and 4 of them are selected and underground. 2 in the LBC, which I'll talk about in a second, and 2 at SNOLAB. And the goal of them is to make background spectrum measurements, in particular try to see if we can verify this excess at SNOLAB. This is what the SNOLAB excess looks like with the current threshold in blue. But if you just extrapolate this excess to low energies and you improve the threshold to 5 electrons with the skipper CCD, then you get a much higher Newton rate of events, so we could actually confirm this over background. And also do the first dark matter electron scattering limits by the DAMIC-M collaboration. So here's the LBC, it's called a low background chamber.
Álvaro, I have a question about this exercise. So then what you're saying is that the thing that you're observing is a convolution of exponential background shape plus, let's say, the effect of the threshold.
Yes, yes.
And that's the blue distribution. So now the threshold is going to be small, so you expect to see a more clear exponential shape.
Yes.
Okay.
So we expect, you're basically correct.
Okay.
So the low background chamber is something that is already in the brand new DAMIC-M clean room at Modan. It's really focused on addressing backgrounds from DAMIC and SNOLAB toward DAMIC-M. So DAMIC-M has a much more stringent radioactive background goals, and we understand very well that radioactive backgrounds of DAMIC and SNOLAB. And so we basically just building a new small system to address that. and improve on the background. So you can see here, there's the internal ancient lead shielding. This is ancient Roman lead. The copper crystal has minimal activation. We have a large copper box that can accommodate even DAMIC-M CCD modules. And we're actually working with, or IFCA is working with Can Frank to get a new electroformed copper lid. So this can be really, really low background. This picture is from like 3 days ago when I was in LSM and I installed these guys that we basically shipped them from Washington to France, and then we came over and installed them, and they were tested at Washington with great success, and they seem to be working quite well. So we installed them this week. Excellent detector performance. These are the people that were there. I am right here. Paulo Privitera, who's the spokesperson, is to my right. And then you can see here the 1/√² suppression at LSM and electron peaks. Now there's only one because the leakage current is quite low, right? Okay. And then also we're installing 2 more at DAMIC at SNOLAB. This has multiple uses, but basically what we have right now, it's 2 DAMIC-M and 2 Sensei CCD skipper CCDs installed. They were installed, I was in Canada before I came to France in October and November, and we installed them there. We had problems with the crack cooler, but so they're not cold and not running yet, but it's been repaired and maybe we turn this on today. And the goal here is to reproduce the background environment in DAMIC at SNOLAB, so we could remake the spectral measurement with lower threshold and really do, in a more direct way, this at SNOLAB. The LBC hopefully is lower background. So we'll see what it turns out. So let me just say that we have these 2 systems. We have new large format skipper CCDs running underground, and we plan to deploy them to start doing science basically now. Okay, any questions about DAMIC? Oh, okay.
Which is the price of DAMIC?
DAMIC-M. Then I don't know. Do you include not like students? You mean like the materials?
The core cost.
Yeah, it's about €4 million. The bulk of the cost really is the CCDs. So let me say that. So this array. Oops. Actually, this array is 52 modules of 4 CCDs. You have 4 CCDs in one 200 millimeter diameter wafer. So these are basically 52 wafers total, but then you have a yield. That's why we have to test them all before, which is maybe 30%. So basically we have to do multiple wafer runs, and we end up with like 700 CCDs that we have to test, and purchasing those 700 CCDs is probably the bulk of the cost. Electroformed copper is also expensive. But cryogenics are easy, so that's clear. Go ahead.
Yeah, about the exponential extrapolation for that excess that you found, why you assume that is exponential if you don't know the origin?
Yeah, we don't know. I'm just saying, if it were exponentially, it would look like this. Okay. The point of this is that we can tell if it's not, or if it's not there at all. I don't.
You said that the rate of efficiency is 30% of the CCDs?
Well, we don't know the number yet. We're going by past experience.
Okay.
Okay. One of the goals of the pre-production run that we're doing now is to estimate what that yield is. And you know how things are going, but it's kind of like collaboration secret right now. Okay. Okay, good. So that's it for dark matter structure. So let me tell you a bit about something that is very early stages. It's something that I hope will be called someday the Selena neutrino experiment. And this is based on the idea of, again, taking another type of detector for a different application and trying to see if we can do something with it for particle physics. So I don't know if you've heard about amorphous Selenium detectors. They're used for X-ray detectors in medical imaging. So often, actually mostly, the mammography they're very popular. There are multiple companies that work with them. And they're actually a large area. They're some 720 centimeters squared and up to 1 millimeter thick, and they have large pixel sizes, 85 micrometers squared. They're made in flat panel displays, so it's basically on glass. They're operated at high electric fields, 10 volts per micron, and you get, the charge yield is much lower than silicon. You get only about 50 electron volt pairs per keV. But you have a large band gap. So these things have picoamp per centimeter squared leakage currents at room temperature. Okay, so that's why they are, even though their charge yield is not very high, because you can run them for room temperature, it makes them very versatile for for applications in medicine, right, where you don't need to have nitrogen-cooled system for your mammography machine. But the limitation was, we look at this, that you have 1,000 electron hole pairs RMS of pixel noise. So you can, even though you can make an image, exposed image, you couldn't see particle tracks, okay? And then there's a very same thing that caught my attention, which is that selenium has an isotope called selenium-82 that is undergoes double beta decay. I'll talk a bit more about double beta decay, but the idea here is that you have a nucleus that emits 2 betas at the same time. And there's a particular process called the neutrino double beta decay process that would be a discovery of new physics. So the idea here would be, let's just make this detector lower noise. So you have amorphous selenium now coupled to a CMOS pixel array where you can have smaller pixels and lower noise. And then you make a big tower of them. You have these electron tracks coming out. You collect the charge in a pixel array, and you make a very high resolution image of it. This is a simulation. We're not even close to there yet. Okay, but then you get basically 2 tracks like these. You can see the Bragg peaks. Okay, there's a double beta decay event. You add the energy, and maybe you can discover this process. So the idea was, can we basically get tracks like we do in DAMIC with something that is a more difficult to work with material in some ways, called amorphous selenium, but has a very special isotope. There is a slide that is missing somehow. 1 second. Okay, no, it's actually there. Never mind. So the idea here is to make a detector that is high energy resolution, so we can perform this precision spectroscopy. As you will see, it's important for double beta decay because energy resolution is what allows you to distinguish the neutrino signal from the 2 neutrino standard double beta decay signal. Excellent spatial resolution, which is what gives us the background radio detection capabilities. In particular, you can distinguish double beta decay events from, say, ordinary Compton scattering gamma ray background because you have 2 Bragg peaks instead of 1. You want this to be easy to build, so it operates at room temperature, and because your background rejection comes mostly from the ability to identify the type of particle and the decay sequence, then you don't rely so much on it being ridiculously radio pure. And then there's one other thing that helps a lot, which is that the energy of the neutrino double beta decay signal in selenium-82 is 3 MeV, which is above most of the backgrounds from natural radioactivity. So it's actually lower, you start with a lower background requirement. And then you want something that is scalable. So we want to build these standard CMOS process, 300 millimeter diameter wafers, and industrial amorphous selenium deposition. These companies that already make the sensors for medical industry, they already deposit about a ton of amorphous selenium per year. Okay, so we would say, and we're working with Hologic, which is one of these guys, bigger guys, and they're being very, I guess, willing to work and helpful. So we started small. We want to make this huge thing, but we started with 1 pixel. This was basically a sandwich of amorphous selenium with 2 electrodes connected to a CMOS preamplifier. So it's a little tiny chip. And we were able to obtain basically the lowest noise, highest resolution pulses in amorphous selenium ever. This is, you can see here, we actually, something that had never been done before that we could do is that because we had such low noise traces, we could distinguish from the pulse shape whether the events were happening in the front or the back of the selenium layer. And we did mostly this to measure what the charge yield and the intrinsic energy resolution of amorphous selenium was, because it's a crucial parameter for neutrino double beta decay. And so you can see here, this is our expectation right now, our best estimate for the energy resolution at the Q value, the 3 MeV double beta decay signal extrapolated from our calibrations with 122 kV gamma rays.
So one question, I'm just curious, is there any electric field there? I mean, because the
Yes, there is an electric field.
Okay, but it's small one, right?
No, it's very high.
It's very high.
Well, it's about, in this case, I think this ones are 30 volts per micron.
Okay, this is really high. But
Yeah.
then, why it takes so long the signal to propagate? It's microseconds. Yeah.
Yeah, this is okay, so this fast pulse, the holes are quite fast, but the mobility, the reason why these two look different, and this is so slow, is because the mobility of electrons and holes is very different between the two of them in amorphous selenium. Holes are fast, so if you interact on the positive electrode side, you drift the holes immediately, and it's very sharp. The electrons, they really lag behind 4 microseconds, and that's why you get this very slow rise.
Yeah, but I mean, you have signal still. I mean, the signal starts at for holes, okay? Just hole injection. The signal is starting around 60 microseconds, right? And 40 microseconds after is still there. I mean, it's still drifting because you still have signal.
Oh no, that's just decay length of the amplifier.
Ah, okay.
Okay.
Fine.
So we have a very long decay length so
Okay,
that we don't
fine.
lose charge.
Okay.
So we can actually get the bare estimate of the energy.
It's a charge amplifier.
So it's only the rise time that depends on these.
Okay.
And okay, so we did this single pixel, then we moved into many pixels. So we started with a chip called Tub Metal 2 that we borrowed from Berkeley Lab, not even designed for us, but it has bare metallic contacts. We deposit amorphous selenium on that, well, Hologic does for us. We put an electrode, and then we, just like that sandwich one, we bias it, and now we try to look at the charge in the pixels. And this is done, there's a little test board that we built for it, and this is our setup at Sandpoint at UW. And we just took their chip, which is, we took it mostly because two things, the bare metallic contacts and the low pixel noise, 15 electrons. And it basically worked. So we were able to improve noise by 50 times relative to a commercial detector. So here you can see the response of a Tub Metal 2 with amorphous selenium with a 20 electron RMS of noise from 1000, right? So we're 50 times, and these are just pixels that collect charge. So you can see here, this is just, this is a CMOS array that is run in rolling shutter mode, so you have a decay of the signal. Anyway, you see nothing, then you see the pixel light up and decay away. This is from an interaction for a cobalt X, right? And then we put the high energy beta source, and then we could see for the first time electron tracks. Okay, so they're not the super high resolution ones that we want to go to, because the pixel size is too big, but you can already see this. So in my not very humble opinion, I think that quantitatively and qualitatively, this is as much of a technological milestone for us as it was, as the skipper was for the dark matter searches. So here the status are, we measured the milestones, we measured the energy response of amorphous selenium, we couple amorphous selenium to a CMOS pixel array. You expect soon a publication with these results. I've been basically busy with DAMIC, but it will happen. And what I want to mention briefly, and I guess I don't have 15 minutes left about, we started a bit late, right? Yeah. Is the prospects of what you could do if you were to build a very large detector with these amorphous selenium sensors. I will mention that this is actually evolving quite rapidly. What ends up being built in the coming years might not be very much what you're seeing here, because we're learning things and changing things, but I'll show you if you just had, with some basic specifications, 100-ton-year exposure with this, what science you could do. So the first one is neutrinos double beta decay. This was the original motivation. So you have the standard process where you have 2 neutrinos and 2 electrons coming out of a nucleus. And then in this process, there's the possibility for the no neutrinos to be emitted. You get only the 2 electrons that carry the full Q value of the decay. And then if you see this, then that's an evidence of the neutrino being Majorana. And the decay rate is related to a few things, including the particle physics properties, basically neutrino, what we call the neutrino Majorana mass, properties of the nucleus, and then something just related to kinematics for the phase space factor. But the crucial things here for looking for neutrino beta decay is that you need a good energy resolution, because you will always have background from the two neutrino channels. So the two neutrino channel is never exactly at the Q value, because the neutrinos will always carry some energy. But the tail of it can come very close, right? So your resolution basically can make the two neutrino channel block your signal. The other thing that is important, and this is the one that I mentioned that is very interesting for selenium-82, is that you want a high Q value, because you have all this. This is actually what a germanium detector sees underground, and most of the background has come from uranium and thorium that I mentioned earlier. And uranium and thorium background especially ends roughly at the thallium-208 line, mostly, at 2.6 MeV. And then you have very little above that. So you want a Q value somewhere around in this region, so your background to start with are low. And then the other nice thing you want for background suppression is to identify is to be able to reject events from, say, Compton scattering and stuff. So you want to make sure that it's a double beta event with 2 electrons. So we have a paper from 2017 when we basically outline the type of science we could do, and this is basically updated in this slide. So if we can identify the 2 electron events from their Bragg peak, so this is 2 electrons, 1 electron, you can see the difference of, this one had a straight start, one of the ends is straight here, these ones are both like struggling, like Bragg peaks. We can suppress the single electron background by a factor of 1,000 with 50% signal acceptance. And then backgrounds in the amorphous selenium, so say from contaminants, uranium, thorium, alpha particles, can be suppressed by particle ID very, very well. And we expect a background that is quite low. Now, our latest simulations, which are very much ongoing on the energy resolution, looks like this. It is what it is. I think we can improve a bit, and I've been working on it. But it tells you at least that this technology can go up to 10 to 28 years half-life searches based on the resolution. And the pixel size that we need for something like this is 15 micrometers squared. And right now, as you said, the ones I showed, the track that we measure in the lab are with 80 micrometer squared pixel sizes. Then something that we've been thinking about also is solar neutrinos. And this was actually motivated by me reading this paper by Jiri and Elliott, which was talking about the solar neutrinos being a background for neutrino beta decays. Now, this is not a problem for us, actually, because we can actually tag and reject neutrino captures in amorphous selenium because there's a spatial coincidence. So the neutrino turns, here it is, neutrino turns selenium-82 into bromine-82, and then bromine-82 goes through a decay chain to go into krypton-82. So because of the same way that we tag backgrounds in DAMIC, we could actually tag each one of these neutrino captures and remove them. But then again, we can also use these neutrino captures to do solar neutrino spectroscopy, because this is a charge current reaction where the prompt electron, the first electron you get, carries all the information on the neutrino energy. This is just neutrino energy minus the threshold value of 172 keV. So if you, this is what we call, so if you tag them and you look at the prompt event, then you get a spectrum of the energy of the neutrinos that are captured in your target. And you know, I talk in this slide a bit about background. So the point here is that because the pixelation is so high, the expected number of accidentals when you're looking to this coincidence is very low. It's less than 10 to the -4 in 100 ton years. So you consider this basically, in terms of accidentals from natural radioactivity, to be background free. Then you have to think, well, what are other ways to make bromine-82 in your target? Traditionally, if you know anything about radiochemical experiments, PN reactions were a problem. But most of the ways that you can make bromine-82, this metastable state, from charged particle reactions, your prompt event will be very different, because it's not just an electron coming out, but you have here some highly ionizing particle. And then, you know, I did a long survey. I put the table of isotopes, looked for cosmic isotopes that could have a decay sequence that mimics this. Really couldn't find anything. And then there's little details about neutron captures and selenium isotopes. But I think that so far, we haven't identified a background that could mimic this very particular, what I call the triple sequence that gives you the neutrino event. So I think it's still possible to perform zero background neutrino spectroscopy with a large selenium emitting detector. And the one that we thought immediately were the solar neutrinos themselves, right? So you have, I don't know how much you know about solar neutrinos, but you have this flux of neutrinos produced in the sun. These are just labels for the different nuclear reactors in the sun. These are predicted by the so-called solar models. The neutrinos propagate through the sun, and then they arrive on Earth, and they have some probability of survival based on their energies. And these are the survival probabilities are determined by the neutrino physics, the MSW-LMA values. And so if you were to look at the prompt event in events in a large selenium detector, you will see this is just with the resolution we've measured already, or what we think the resolution should be based on our measurements. You have PP, CNO, beryllium-7, PEP, and you have these two lines, right? Beryllium-7 and PEP, which are more energetic from the sun, come out as lines in this large detector. And here is just an idea in 100-ton years, what would be the statistical uncertainty just by doing a counting experiment in different energy regions. Okay, so what could you do with a result like spectrum like this? So first of all, there's solar physics. By measuring PP precisely, you could get a strong constraint on the solar luminosity, the neutrino solar luminosity, that tells you that this often compared with the photon luminosity to see if there's any forms of dark radiation, things like this. Then there's the solar metallicity. I don't know if you've heard, but the CNO neutrinos, they are very closely related, their fluxes, to the amount of carbon and nitrogen and oxygen in the sun, which is their discrepant measurement from other ways. And this is called the solar metallicity problem. And so the CNO flux measured to 13% would be able to say something about the solar metallicity when the different model predictions are about 28% apart. And then this is one thing that is probably quite unique to this, is that because you can measure the position of beryllium-7 and PEP lines, the position of these lines are related to the temperature in the core of the sun. So here it is just the values of the line difference, and you can measure it by about 26%. So you get a 26% measurement of the temperature of the solar core. And then there's a bit of neutrino physics you can do. So especially this PEP line, when you can measure the PEP flux to 8%, you could basically see if there's any deviations from these survival probability from the MSW-LMA prediction. So in blue, in teal here, this is the more CNO measurement, and we could do that much better. Okay. Now we could still not tell these two different scenarios, particular scenarios from non-standard interactions, but for sure you could constrain this much better. So I think it would be a sensitive probe for neutrino transport to the sun. Okay, so here's my conclusion. High resolution pixelated solidity detectors are a promising technology for extraparticle nuclear physics. DAMIC is about a decade old, and the program is very well established. We've had quite a few PRLs, and we finished what we were set to do. Now we're building DAMIC-M. I think we're going to be bringing the CC dark matter search experiments to the forefront in sensitivity, both in dark matter electron scattering and dark matter nucleus scattering. There's quite a bit of progress underway. As you saw, we're already testing these sensors, deploying them underground with very good performance. So you expect science for sure next year. And then we have this new thing called Selena, which is another adventure sort of for trying to use a new type of sensor to do a spectroscopy of double beta decay and solar neutrinos. And I think, again, our R&D is quite well, and we have achieved the first significant milestones, and maybe we'll be moving forward to make something bigger in the future. Thank you.